Hello and welcome. In this video, we're going to take a look at a vector function. Now, this is kind of like an extension of a normal function, except that because it's a vector function, it doesn't just produce some sort of number, it produces a vector. And that can be an n-dimensional space. Now, once you've got a vector, you can think about that as defining a position. Position can give us points, and when we have a whole series of points in n-dimensional space, then they can form a curve, and we call that a space curve. So let's start off with the definition here for what a vector valued function is and see how that takes us into the realm of space curves. So a vector valued function, let's say r of t with a little vector arrow, that's a function where we're given an input which is simply r. So it's actually like a one-dimensional input, and it gives us a unique vector in Rn. So as an example, in three-dimensional space, R3, we could maybe have this function as being like a component-wise three functions, ft, gt, and h of t. I've got those three functions for each of the components. And by choosing a value for t, that's going to get us a vector in R3. Now what we can do with this is we can treat each of these vectors as a position vector for a point, and then define a space curve. So let's specifically maybe focus on this R3 example. Well, let's start off with f, g, and h being continuous functions over some sort of interval. And let's let all of these points defined by that position vector r of t just be a set of coordinates x, y, z for all of the values of t in that interval. That's going to form what we call a space curve. And the space curve basically can be written like this, or it can be written as a set of parametric equations. So we could split this out into multiple equations as well. We could say that x is f of t, y equals g of t, z equals h of t, and each of these would be a parametric equation where t is the parameter. Now, much like with functions of even just a single variable x, let's say, when we have f of x, we talk about what's happening to f as x increases. So it has a natural direction. Same thing here with a space curve. We want to take a look at what's happening to space curves as t is increasing, so space curves kind of have this natural direction as well. Now, if we wish to try to visualize the relationship here between the vector function and a space curve in three-dimensional space, well, I can tell you right now that my drawing skills are going to be a little bit limited on a single page here. So why don't we turn to some software here and see if we can kind of visualize what is going on when we talk about a vector function and the associated space curve. So we'll flip over here and we'll take a look at Maple, which is some pretty useful software for this kind of purpose. So here I've got a Maple worksheet. I've already prepared a bunch of commands, and a lot of the three-dimensional plot tools aren't included by default, so I have to just include those. Now here's an example. I've got a function r of t, which is cosine t, sine t, comma t. And you'll maybe recognize the parameterization of a circle from those first two components. This is now a little bit new here. This is in a third dimension. So as t increases, the z component is increasing. Now this next line here is nothing more than I'm just going to set sort of an arbitrary domain for a to b being from 0 to 2 pi. And I had a little bit of issues. I had to make 2 pi a decimal here, but that might be just my own limitations with Maple. And I'm going to basically just plot several vectors. I'll plot 12 of them, so I'm going up by small steps here. Now this first plot here, I'll show you. P1, this first plot, these are several vectors. So starting at when t equals 0, if we plug that in, you can see the vector is simply just 1, 0, 0. And sure enough, it is, well, maybe let me change the axes here. It might be a little bit more useful in this sort of form. In our first octant view, you can see that the first vector down here, this sort of orangey colored one, is in fact just 1, 0, 0. Now, as we start increasing t, and I'm going from 0 to 2 pi by steps of 12, so I'm going up by pi over 6. Pi over 6 being kind of nice. You can see that it's going to be sort of like all these special triangles as we go around, and you can see how the z coordinates are increasing. So these are vectors in standard position, and each one of those is going to define a point on the space curve. Now, let me, first of all, I should mention that's the arrow command in Maple. Arrow is basically what it sounds like. It's plotting vectors as arrows with a lot of these options so that the arrows looked manageable and very colorful. You can always change the color so they're all the same color. But I'll leave them like that because I'm going to plot another graph here, which is the space curve. And space curve defined by that same vector function, again, just from 0 to 2 pi. Now, I have the option here to display that graph, or I can display both at the same time. And that's what I'll do. Here you can see I've got the same vectors. And while the space curve is including all of the values of that vector valued function from 0 to 2 pi, and so you can see that the tip of the arrow is tracing out a path. That is a space curve. And so we can decide, what A and B is. This thing would continue upwards. I could just change this so I go one more revolution around a circle, change the display, and you can see I'm still using 12 steps, so the vectors are a little more spaced out, and I've just gone around the circle one more time, and I've also increased my z coordinate. And this is what we would call a helix. So that's the association between a vector valued function and a space curve. We can leave the space curve as a set of parametric equations, or we can just say that a space curve is defined by a vector valued function such as this. There we go. So you can kind of see this, obviously some major uses for having some software. You could try to graph this on a page, but it's going to be pretty difficult to try to get that perspective right. So yeah, using some software here is probably going to be super helpful. Okay, let's take a look a little bit more here back at the notes then. Now, space curves can come about from many different applications. A very straightforward application would be just taking a look at maybe where two surfaces would intersect each other in three-dimensional space. So let's pick two sort of common shapes here and see how they would intersect one another. All right, in this example, let's take a look at some classic surfaces. 4y equals x squared plus z squared, and y equals x. Now, these are not exactly intuitive necessarily. If you've had some experience, then you probably recognize that when you have something like y equals x, and one of the variables is missing, that this would be a cylinder. Now, it's really just a line, y equals x, and so when you take a line and you project it along the z-axis, well, it's probably not the best thing to call it a cylinder. It's a plane, y equals x, and then it runs parallel to the z-axis. So we have a plane. Now for this first equation, x squared plus z squared, that might seem a little bit like a circle where we have 4y be the radius squared. Now, of course, this is just y, so this isn't exactly an intuitive shape, but you can think about 4y as y is growing here. The radius would be increasing. So it's definitely some sort of circular object that is growing along the y-axis. And we have parabola type of shapes in our xy planes and zy planes. So we call this a paraboloid. Well, the first step here that we can really apply in order to get the curve of intersection is just to think about what is an intersection of two surfaces. And well, it's the set of points that would satisfy both of these equations. So that's what we're going to do, is we're going to take these two equations and we can merge them together, because every point that satisfies y equal x has to also satisfy 4y equal x squared plus z squared. That means that y equals x is a simple substitution that we can make. So we'll start there. All right, so we've got a substitution for x equals x squared plus z squared. Well, this would define points that are the intersection of two surfaces. Now, in order to get a curve out of this, we're looking for a parameterization for x, y, and z, where we can simply have t be maybe some interval. And we kind of recognize that if we take a plane and we cut it through a paraboloid, well, chances are we're going to get something not necessarily circular, but maybe elliptical. Well, we'll see what happens here. Let's take a look and see if we can make this shape recognizable in a standard form. And here we've got an x squared and a z squared, but we also have an x term. So it may not be jumping out at you, but by completing the square, we should be able to see that this is actually a circle, but it's not centered at the origin. Well, first we'll get all the terms on one side, and then we'll complete the square. Now, if it's been a while since you've done some completing the square, don't worry. I believe I have a video of that in my pre-calculus section that you can take a look at. Now, thinking about this as just being only projected onto the xz plane at the moment, and we can just ignore y, we'll bring it back in a moment, but if we just project this onto the xz plane, we see that this is a circle that has a radius of 2, and it's centered at a point where x equals 2 and z is equal to 0. And that is something that we can parameterize. it might be helpful just to remember that the parameterization of x squared plus y squared equals r squared on the xy plane is simply x equals r cosine t, y equals r sine t, and t being any value from 0 to 2 pi. And that just comes from trigonometry. So to get the parameterization of this projection of this intersection onto the xz plane, we will have x equals simply a shift 2 plus 2 cosine t. Since the center is not at x equals 0 and the center is at 2, we just need to move everything to the right by 2. And this is the xz plane. So instead of using y equals r sine t, we have z equals 2 sine t. Now that's going to give us a circle on the xz plane. But we want this circle, which we've projected onto the xz plane, to exist on the plane y equals x. And that's pretty straightforward to do because now we know what x is parameterized as. Y equals x, and that gives us all of the parametric equations that we need. Again, this is just going to be only necessary for t to go from 0 to 2 pi. Otherwise, we'll be tracing around this curve of intersection multiple times. So putting all the pieces together, we simply just need to add in that parameterization for y. And y equals x, so y is also going to be equal to 2 plus 2 cosine t. All right, well, let's go take a look over here at Maple again. So I've got quite a few commands loaded up here once again, and in this case you can see I'm using implicit plot 3D and I'm using the space curve command. And the implicit plot 3D command is going to be so that we can plot the surfaces, and the space curve command is just so that we can plot the nice little curve of intersection. So we've got the two surfaces, and I've chosen some values of x and y that are fairly convenient. I mean, I happen to know roughly what the maximum x and y values are for this curve of intersection. So things are kind of based off of that. And I've added some extra options for some pretty colors and to make them relatively smooth and get rid of the surface gridding. So that's what those first two commands are. And then the space curve, you can see I've just got a list of the 3 parametric equations with a nice blue curve. And we'll plot that. And it's, well, not too bad. You can see there is a nice little intersection of green and red surfaces, the plane and the paraboloid. And there is a faint little blue ring here. That's the space curve. Now, it might help if I take this surface and I make it half transparent. There you go. You can really start to see where that blue curve comes from. Well, there you go. That kind of confirms that that is, in fact, the curve of intersection of the two surfaces. Now, using this idea of having two surfaces intersect each other to get a curve can be used kind of in the reverse direction as well. If you don't have software handy, what you can always try to do is if you, say, have 3 equations for this parametric equations, x equals f of t, y equals g of t, and z equals h of t. Well, if you want to try to visualize that without software, you might be able to take 2 of those equations, the one for x and one for y, for instance, and treat that as like a system of equations where you want to eliminate the parameter t. Then you get an equation that's x and y, and that will give you a surface. And maybe then take the equations for x and z, or y and z, treat that as a system of equations, eliminate the parameter t, and you get another surface. And if you can just think about a curve, one way to maybe visualize it is see whether or not you can find 2 surfaces that would intersect each other to get you that curve. So that's just another way to help out, at least anyways, if you don't have software, although software is definitely the way to go. Well, hopefully that helps you kind of understand what a space curve is and how we represent it. And one way to represent that is using a vector function. And we're going to see very soon that with vector functions, we can take a look at things like derivatives and integrals, because it's just a function of t. It's actually pretty straightforward because we're treating it as a single parameter function. So it's kind of a little bit like single variable calculus. But we'll save that for the future here. Thanks for watching, and I'll see you in the next video.